this is lab 4, oscillations. So the purpose of this lab was to model the motion of an oscillating spring mass system swinging in an arc. And so the fundamental physics principles used here are Newton's second law, which states that change in momentum with respect to time equals net force, and the energy principle, which says that the change in energy is equal to the work on the system plus the change in thermal energy. And so we're not worried about that for this particular case. So really, we're using the change in energy equals the external work on the system. And so the results were that the energy of a system with no external work acting on it remains constant. So this is the experiment. The initial conditions are that a hanging mass attached to a spring is let go from rest to swing in an arc. And we made the system, the mass, the spring, and the earth. And so there's no external work on this system. So from that video, I extracted tracking data for the X and Y positions. So from there, I was able to set up this code. The mass is given. The position and velocity are both extracted from the experimental data. So I made the origin the attachment point. So that's where this initial position comes from. And since it's let go from rest, this is the initial velocity. The spring constant was calculated using this formula, which is the formula for an oscillation period, and this was used to calculate K. I was able to calculate the oscillation period by taking the average of a few oscillation periods, rearranged for K. We were able to solve for the relaxed length of the spring because at the bottom of the arc, there's no change in the y momentum, so we can set the net force in the y direction equal to 0 and isolate the relaxed length, and we used L equals 0.7, which is given to us. So from there, I calculated all of the initial energies using these formulas. Kinetic energy equals 1/2 mv squared. This is the formula for gravitational potential energy near the surface of the Earth, and spring potential energy equals 1/2 ks squared, with s being length minus relaxed length. So we defined these as the initial energies, and from there calculated the net force acting on the mass, and using Newton's second law updated the velocity and the position. With this new velocity and position, calculated the current kinetic, gravitational potential, spring potential, and total energies, and then calculated the change in energies. And so here were the results for the X position and Y position of the model versus of the actual experiment. And here was the graph for the changes in energy versus time. And so while all the different types of energies are changing, the total energy is constant. Some potential source of error here is I manually tracked this data, so it's not perfect. The video was kind of blurry. It's hard to get it right in the center. And also, I did not account for air resistance in this model. So there actually is some external work being done that would cause the system to lose a little bit of energy, and I believe that's why the oscillations are slightly smaller. So the energy principle was satisfied for this experiment because the total energy of the system remained constant, and this is what the energy principle states will happen if there's no external work acting on the system, which is what we're assuming here. The oscillation period calculated using the data for the X tracking was 1.661 seconds. Using the data for the Y tracking, it was 1.5195 seconds. So these are close, but there is some slight deviation there. So it's not completely perfect.